you for specific resistance, like the resistance of one of those loads. In this case, because it's parallel, we can just take the resistance and multiply it by 4. That will give us our total resistance. Do you guys want me to go over that, finding the resistance of a single one given this question? Or do you think you guys have a good handle on it? Go over it? It's divide by 4 if I have one element and I'm looking for a total, but if I have a total looking for one element, it's multiply. Let's talk through that logic problem real quick. So in this question, if I want to find the single resistance of one of the elements, then I know that my back up. In this, R total is equal to 1 over R1 plus 1 over R2 and so on. And it all adds up to 1 over 4 over R1 because they all have the same resistance. If they're all equally rated identical loads, this would be the resistance formula that we would come up with. In this, it's just dividing two fractions by each other. We have a top and a bottom fraction. Let me take all of this stuff, move it down over here. This is really what's connected to the problem. The top right over here is extra steps, just so everybody's on the same page. I'm going a little bit further explaining the single resistance, single element resistance. In this, 1 divided by 4 over R1. 1 is really 1 over 1. It's the same exact number in math. Because we're dividing, we can cross multiply or multiply by the inverse, flipping this second one here, multiplying straight across. We get R1 divided by 4 equals R total. Now, if we have our total 24.732, and we know that R1 divided by 4 equals that, if I want to find R1, I'm going to multiply this right side by 4 to cancel these out. If I do it to one side, I have to do it to the other, multiply by 4. So I take 4 times 24.732. And I'll get 98.929. And this is going to equal R1. So that's how you figure out how or what the resistance is of a single element if they're in parallel. They all have to be identical. If they're not identical, it doesn't work. Now, this is a little bit of extra math on top of it. Again, just be prepared if they do ask the question. Going on to number 6 here. Let's move that up. Number 6, refer to the figure above. How much current will flow through each hot circuit conductor? All right, so if we're looking for how much current is going to flow through them, we need to figure out how much current is on each of these loads. Well, let me back up. The connection of this, because it's all orange under one and all blue under another, I know that this is parallel. It's a color to color type connection. So all of them look like this. Connected through in parallel. Top is blue, bottom is orange, however you want to say that. So we're in parallel here. In parallel, I know that my I total equals I1 plus I2 plus I3 3, just like that. So if I know that my amps add up, I can just figure out how many amps each of these loads gets, and then I can use that and total them up. I can just go off of my nameplate here and take my nameplate as gospel because my panel says 240. All of my nameplates say 240. So all the information I get off the nameplates is good information. Load 2 says 7.8 amps. That's a quick, easy one. Load 1 and load 3 both have kilowatts. We just need to convert those over into amps. The way we do that is I equals P divided by E. So in this case, we're going to take 2,300 watts divided by 240. And this is load 1, and load 3 is going to be 2,200 divided by 240. Plug those guys into your calculators, then we'll get those answers rolling. Oh, you guys can't hear me. I'm sorry about that. Yep, I'm getting exactly the same numbers that you guys got. So all we need to do now is take all those numbers and add them up together. So we'll take load 1, 9.58, plus load 2, 7.8, plus load 3, 9.17. And I got a total of 26.55. 26.55 delta right there. All right, moving on to number 7 here. I'm going to clear off the board. Number 7, a bathroom vanity lighting fixture will draw blank amps when connected to a 120 volt branch circuit. The fixture has 24 lamps installed. Each lamp has a rating of 40 watts at 120 volts. All right, well, when we're installing these fixtures, we need to take a look at the rating. The rating is 120 volt and the branch circuit is 120 volt. Because these match and because in parallel E total equals E1 equals E2 and so on, this is what I want to achieve. If I have a branch circuit of 120 and my lamps want 120, I want to be in parallel. I want to put them, I want to hook them up that way. So because I want to hook them up that way, I can use all of my parallel rules. In parallel, I know that my power total is P1 plus P2 and so on and so forth. Because that's true, P total equals P1 plus P2. I have a rating of 40 watts for each of these lamps. Because each of these lamps is 40 watts and I have 24 of them, I'm just going to take 40 times 24. 40 times 24 equals 960. And this is watts total. Yep, 960 watts. With this watts total, I'm looking for amps. Amps total equals P divided by E for this problem. I don't have anywhere to share the recording, unfortunately. Yeah, sorry about that, Kyle. I don't have any way to share the recording with anybody. I have like the chat and all of that stuff, but I don't know about the audios and everything. But we'll take 960, not 920. 960 watts divided by 120 volts as prescribed by our branch circuit. 960 divided by 120. Yep, 8 amps. And 8 amps is going to be our answer, E. All right, number 8 here. When a single car garage is attached to the house, the NEC requires the garage have at least blank receptacles installed inside of the garage. All right, let's take a look at this question. First off, we're looking at a single car garage in a house. All right, single car garage in a house. Next, we're looking for receptacles inside of the garage. This is the number of receptacles, not the protection of them, but how many receptacles there actually are. If we think about where in the code we might find this for another thing, we might come up with 210.52. 210.52 gives us our required receptacles in a dwelling. Let me pop down there. Okay, so 210.52, and let's look through and see if they require anything in the garage. If we come over here to part G1, so G is basement, garages, and accessory buildings. Part 1 is garages. In attached garage and in each detached garage with electric power, at least one receptacle outlet shall be installed for each vehicle bay and not more than 5.5 feet above the floor. So we can go back over to the review, and we know that when a single car garage, a single vehicle bay requires one receptacle. All right, we look at our answers. 2 on opposite walls, no. 2 on adjacent walls, no. 1 on any wall is what we're going to go with. All righty. Clear all those drawings off. Let's move down in the review to number 9. Number 9, a GFCI receptacle blank permitted to be located directly behind a freezer in a residential garage. GFCI receptacle blank permitted to be located directly behind a freezer. Let's take a look at our code. We know GFCI protection is 210.8. We'll pop up there. .18. .8, there we go. So behind a refrigerator or a freezer in a garage, let's take a look at our requirements. Ground fault circuit interrupter protection for personnel required. So this last sentence here, if you read through the beginning of it, this is the sentence we're looking at. We need to provide it as required in A through F. The ground fault circuit interrupter shall be installed in a readily accessible location. Behind a freezer is not readily accessible. You would have to move the freezer to get to the ground fault circuit interrupter. So because it's not readily acceptable, it would not be permissible. So we take a look back at the review, is not permitted. Number 10, type UF cable installed in PVC under a building must be blank inches deep. If we're looking for a depth of a conduit, then we're going to be looking at cover requirements, 300.5. 300.5 is our burial depth or cover requirement section. Um, 350, 300.5. All right, and now let's take a look at what we have. It's type UF cable, direct bury cable in PVC underneath of a building. So because it's in PVC, that PVC is protecting the cable. And we can go over to column 3, non-metallic raceways listed for direct burial. So because those non-metallic raceways, that PVC is there, that's why we're using column 3. Under a building would be row 3, and it's 0 inches. C, 0 inches. All right, number 11, rigid metallic conduit under 4-inch thick. UF would Yeah, so if it was just UF cable and it didn't specify PVC, it would be column 1. Now, with that, it's kind of the same thing, column 1 and column 3, because type UF cable can't be buried under a building unless it's in some kind of raceway. So realistically, your type UF or your direct bury cables would be protected by something else anyway. But moving on to number 11, rigid metallic conduit installed under a 4-inch concrete slab with no vehicular traffic must be installed at least blank inches deep. Same section, burial depths, keep it on, keep it on. We have rigid metallic conduit, which is column 2, rigid metallic conduit, and we're under 4-inch thick slab of concrete with no vehicular traffic. That's the big one that they added in, no vehicular traffic, and that is row 4 right here. Under 4-inch thick slab, no vehicular traffic, 4 inches. We can take this info, go back over to the review, and we have B, 4 inches. Alrighty, popping on to number 12 here, refer to the figure above. Each luminary or head has a lamp with a rating of 150 watts at 130 volts. When all lamps are operating at 120 volts, the current will pull blank amps, or the circuit will pull blank amps. All right, in this question, we have a nameplate voltage of 130 and an applied circuit voltage of 120. Because these are different, we have to find the resistance. All right, we'll break this down into resistance here. R equals E squared divided by P. This is going to be 130 squared divided by 150. Remember, when you're finding the resistance of an element, going off of the nameplate here, you use the nameplate voltage. Once you find this resistance, then you can throw away the nameplate. So 130 squared divided by 150, what'd you all get? Those are wildly different. I think it's the 112. Let me retype it into my calculator. Yeah, 112.6 repeating. So we'll go 667, 112.667. And this is ohms. Now we need to find our resistance total. We have 5 lamps here. There's 2 ways of going about this. You can use your calculator and go 1 over the resistance and then do the whole calculator method. Or we can take a step back and see that all heads are equally rated. If all elements are equally rated and in parallel, you can divide the resistance of one head or one element by how many elements we have. So we have 1, 2, 3, 4, 5. I can take 112.6 0.667 divided by 5. And this is going to get me my resistance total. My resistance total there is going to be 22.53 repeating. Just going to go 5.3. All right, that's our total resistance. Now that we have our total resistance and I'm looking for amps, I know that I total equals E total divided by R total. So my E total, 120 volts, divided by my R total, 22.53 ohms, equals I got 5.326. Everybody agree? 5.33, nice. Yep, this is in amps. A 5.33. Now, if we remember back to the previous question that I did about finding the specific resistance of one element, it uses the same exact logic train with the math. Because they're all equally rated, you can just do that little breakdown. Alrighty. Popping down. Now for these questions here, I would definitely suggest building out a peer chart. I'm not going to build out a peer chart for this one just because it has 2 questions, but I'll see. Do we have another one of those? Dang, we do not. What I'll do is I'll go through and answer this one a little bit quicker just because it has 2, and at the end I'll circle back and show you guys how to build out a peer chart. I would highly recommend doing a peer chart for these questions that are longer than like 5 questions or 3 questions. 3 questions and more, it's just quicker to do a peer chart. All right. In this, it's asking what is the washing machine amp or of current, or amp pole, I should say. Number 14 is the watts of power consumed by the washing machine. So we're looking at the washing machine solely in this instance. Because we're looking at the washing machine just by itself, what we can do is see that this is ran in parallel with each other. Excuse me. Because it's in parallel, we know that the E total equals E1 equals E2, and they give us that voltage of 240. Because we have that, we just need to find the washing machine resistance, and then we can figure out both of these questions here. All right, the nameplate is 220, so we have to find resistance no matter what. We have amps, we have volts. R is equal to volts divided by amps. So if I take 220 divided by 7.2, this will give me that resistance there. Then I can use that resistance and my actual applied voltage to answer my 2 questions. 220 divided by 7.2, I got 30.5 repeating. So we'll go 556. That's ohms. Now we want amps I and P watts. Amps is equal to E divided by R. P is equal to E squared divided by R. Now, when we're looking for resistance, we use the nameplate. When we're looking for actual answers to the question, we use the applied voltage. The applied voltage in this case is 240. So 240 divided by our 30.556 will get us amps. And if we go 240 squared divided by that 30.556, we will get our power. You could just go through, find amps, and then multiply it by the voltage again if you wanted to just get your answers straight by each other. That works all the same. 240 divided by 30.556, we'll get 7.854 amps. And then if we do the other one, 240 squared divided by 30.556, we'll get 18.85 watts. And 7.85. 240 because that's the applied voltage in the question. We can see at the panel it says 240 and on the voltmeter it says 240. These ones are taking into the assumption that the figure tells you the voltage, so they don't say it in the question. Just be looking at that picture because it does change. They might have 240 here on the review, and they might have exactly the same picture, exactly the same nameplate info, but they change it to 208. Just be aware of that. All right, clearing the drawings off, moving on down. We're now at number 15. Refer to the figure above. How much current will flow through each circuit conductor at the circuit breaker terminals to the load? So this is what is our amps total. Current flowing through each circuit conductor just means, hey, what's the current here, which is I total. In this question, they give us a whole bunch of loads that are rated at 240, but we're applying 208. What I want to do is find the resistance of each of these, get my parallel resistance. I know it's parallel because it's a color-to-color connection. Excuse me. Having some weird hiccup thing going on. But it's a color-to-color type connection, so I know that this guy is in parallel with each other. So finding the resistance of each load 1, load 2, and load 3. For my kilowatt sets, it's going to be E squared divided by P, just standard watts, to equal R. And then for the amps, it's E divided by I equals R. Plug those in, get me a load 1, 2, 3 resistance, and then we'll go from there. All right, so Kyle got us here. We got 25.043. We have 30.769. And we have 26.181. In that set there, we can go into our calculator. We're going to have to use our 1 over x method. So what I'm going to do is I'm going to type 25.043, press 1 over x, and then press the plus button. I'm going to type in my next one, which is 30.769. Press my 1 over x button, press the plus, type in 26.181 1 over x, press equals, and then press 1 over x again, and then that got me a resistance total of 9.039 ohms. Does everybody agree? Once I have gone through all the examples, I'll do the peer chart, and if you guys want me to go over any of the different what do you call it? Different steps for like the calculator or anything, you can ask me then as well. All right, now that we got that resistance total, we can plug it into this final equation here. I total equals E applied divided by R total, 208 divided by 9.039. 25.32, Chris. Does everybody agree? Oh, I definitely typed in the wrong number. 208 divided by 9. I got 23.011. Did I type that in wrong again? 208 divided by 9.039. Yeah, I'm getting 23. Chris, did you take 240 by chance? Take a look back, make sure that you're using 208 because our voltage applied at the panel is different. Sweet, sweet. Yep, 23.011. With that, we have to look at our question and get to the closest that we can, which is going to be E23.12. This is slightly off from what we calculated out, but it's all just a small rounding error. If you had two questions that were super close to each other, or two answers that are super close, you might want to do the math again. But sometimes those small rounding errors just make it a little bit different. All right, taking a look at it 16 here. A clothes dryer contains two heating elements that are connected as shown in the figure above. Each element is rated at 2500 watts at 250 volts. The total resistance of the clothes dryer is blank ohms. All right, so we have two elements connected in parallel with each other. And we know that each element is rated at 2500 watts at 250 volts. So what I want to do is R total equals my inverse resistance. But to find that inverse resistance and do all of that, I need the resistance of a single element. So R equals E squared divided by P. 250 squared divided by 2500 watts. All right, I got a resistance of 25 ohms. 25 ohms for a single element. If I'm looking for my resistance total, I know that both of these elements are equally rated, so I can take the resistance of 1, 25, divided by the number of elements, 1, 2. 25 divided by 2 equals 12.5 ohms of resistance. You could also just do 25 1 over x plus 25 press 1 over x equals, and then press 1 over x one last time, and you'll get 12.5 as well. Moving on to 17 here, does the NEC permit a 2-pole circuit breaker to be used as the disconnecting means for a 3.3 kVA 240 volt single phase air compressor? The equipment is installed in the electrical room and it is within sight of the circuit breaker panel board. Let's clear this off. Let's take a look at the code. So for this question, it's asking about an air compressor. An air compressor is a type of appliance. Let's go down to our appliances in 422. And if we remember anything about 422, it's that 422.30 is our disconnecting means for appliances. So 422.30 up here, general requirements. 422.31 is disconnection of permanently connected appliances. So appliances that are rated over 300 volt amps. We know this because it's a big air compressor. For these permanently installed appliances, the branch circuit switch or circuit breaker shall be permitted to serve as the disconnecting means where the switch or circuit breaker is within line of sight of the appliance or capable of being in the locked position. For this, because the equipment is installed in the electrical room within sight of the circuit breaker panel board, then yes, it is permitted. Let's take a look at 18. A water heater has a nameplate rating of 5 kilowatts at 230 volts. The water heater will draw blank amps when operated at its rated voltage. So if it's at its rated voltage, I can take that nameplate as gospel. We take our amps is what we want to find, and amps is equal to P divided by E. In this case, they give us that P as 5,000 watts divided by our volts, 230. What does that get us, y'all? I do agree, 21.379. All right, so 21.379 is, so we have 21.74. Oh, the last article was 422.31b. I think it's 739. I put 379. Yeah, I flipped those around. Yep, 21.74 for 18 here. Moving on to 19, I'm going to clear off the board so I can move this guy up. 19, with the switch in the position below, the voltmeter will indicate blank volts. For these questions, it is a little tricky. Taking a look at the picture, this is a closed switch. They'll try to make it a little obvious, but sometimes it's a little tricky because this is touching, it is closed. If it was up and you could see a space in between the terminal and the lever, that is open. Now, in a closed switch, there is no difference of potential between one side and the other. It is the exact same voltage, so you don't have a reference point. In all closed switches, you'll be reading 0 volts. In an open switch, because there is a difference of potential between the terminal connected with power and the terminal waiting for power, because these don't have the same voltage, you will read whatever is on the voltmeter. Whatever is on the voltmeter is what you'll have on an open switch. In this case, because it's a 12-volt battery, it would be 12, but the switch is closed. Closed switch, 0 volts. Open switch, voltage of voltmeter or power source. Moving to number 20. Number 20, refer to the figure above with the voltmeter leads placed on the terminals on the luminary. The meter should indicate a reading of blank volts. Switch 1 is off and switch 2 is on. All right, if we're putting our terminals here on the luminary, if the luminary receives power, we will see voltage. All right, so let's see if it receives power. We can take this black wire that's on the terminal, trace back the black wire. The black wire goes to switch 2. We know that switch 2 is in the on position, so we can go to the other side of switch 2 and it goes to a blue. This blue comes back up and goes out to our home run to the panel, so we will see voltage. We do see voltage there. Now, how many volts are we going to see? This question's a little bit tricky because they don't outright tell you, but they give you a receptacle. And this receptacle here is your NEMA 515, and it's rated for 15 amps at 125 volts. So on a normal circuit, it'd be 120, which is the voltage that you would see. It is a little bit tricky, but it's a normal duplex receptacle rated for 15 amps. If it's our normal receptacle, it's our normal voltage for it. It is a little bit of an assumption, but I think you guys got that. All right, 21. Two 20 amp small appliance branch circuits required for the kitchen and dining room area are intended to supply blank appliances. Under 1/3 horsepower, countertop, fixed in place, or all of these. Well, these small appliance branch circuits are countertop receptacles. That's the main thing that they're there for. Let's take a look at our code book. Sorry, I'm just scrolling through the code. Give me a second. So if we're looking for what those receptacles serve, we're going to be in 210.52. Man, there's a lot of code book to scroll through. $220. All right, 210.52. All right, if we're looking at section C, gives us our countertops and work surfaces in kitchen, pantries, breakfast rooms, dining rooms, and similar areas of a dwelling. Receptacle outlets for countertop and work surfaces that are 12 inches or wider shall be installed in accordance with the section following, but not considered receptacle outlets as required by 210.52. That's all cool. But the small appliance branch circuits have to be installed as a part of that countertop work surfaces section. So if it's a part of that countertop work section, then it is countertop appliances. I think you could also look at 210.11c for that breakout, because that also requires your small appliance branch circuits there. That can also help. Oh, have I been paused this entire time? Sorry about that. I'm here in the code. 210.52C countertops. It doesn't specify anything about a certain horsepower or fixed in place. It just says countertop. All right, moving on down. Number 22 here. Yep, 210.52C. Number 22, the current rating of a 1725 watt 120 volt heat vent light unit is blank amps. So they don't say anything about an applied version here. They just say the current rating. If it's the current rating, that means whatever the nameplate says, that's what we can get off of it. So we're rated at 1725 at 120 volts. Let me get my pen out here. I know that I equals P divided by E, 1725 divided by 120. I got 14.375. Do you guys agree? Boom. Number or letter A, not number A. That doesn't make sense. All right, we're going to clear up the board here and pop on down. We got 23. How many 12-2 cables enter the wall-mounted switch box in the figure below? Now, if it asks for how many cables enter the wall-mounted switch box, we have to look at the wall-mounted switch box, this big guy down here. We can count up each of these raceways. Come back here. Each of these circles is a cable type and would be considered a 12-2. So we have 4 from the ceiling mounted unit and we have 1 from our home run. So in total, I have 5 cables entering that box. This one's just counting up each of the circles and making sure that if it says wall mounted, you go to the wall mounted. If it goes to ceiling mounted, you just look at the ceiling mounted. Clearing those off. Popping down to 24 here. 24 in the figure above, switch diagram blank is correctly connected, so all the following are true. This one is just look at each of the different points and start following them out. Point number 1 here, the night light is on and the lamp is off when the LT switch is in one position. All right. And the second point, night light is off when the lamp is on, and the lamp is on when the LT switch is in the other position. So if this LT switch has 2 choices to it, we're going to be looking for a 3-way type switch, right? A double pull, single throw switch. In that, we can take a look at our light and night light, follow them back. We have a night light, comes over here, comes up to this wire nut, that goes to constant power. Night light on constant power does not fit this diagram or this situation. If we look at number 3 here, night light comes on over to a switch. That's cool. Light comes over to the same switch. That's good. Now we have a common that goes back up to power. All things are looking good for the first 2. Number 2 here, or diagram 2, night light over, good. Lamp over, that's good. Constant power. Number 2 is looking all right. Number 1 here, night light, light, both on the same single pull, double throw switch. I earlier said double pull, single throw. That was incorrect. Single pull, double throw. Mixed up my letters. All right. Now that we know that 4 is not an option, but it's down to 1, 2, or 3, let's take a look at our other set. The fan can be turned on only when the heater switch is on. Fan can be turned on only when the heater switch is turned on. That means that that fan is dependent on the heater being on. If the fan is dependent on the heater being on, then the heater switch, that load side, should be hooked up to the fan switch. We'll take a look at number 3 here. The heater load side, this red wire, just goes to the heater. It doesn't hook up to my fan. My fan switch hooks into constant power and can be operated independently. So we can cross off number 3. Number 2 here, this red wire is the load side of that heater switch. We come over, it only goes to the heater. But what we do see is this purple wire goes over to the fan switch. That fan switch is fed with constant power. In diagram 2, the heater can only be turned on when the fan switch is on. So this is flipping it backwards, right? If it's flipping it backwards, it still doesn't satisfy, so we know 2 is out. We'll look at 1 here. Number 1, heater switch is going to be red, the switch leg, and we can see that that load side is hooked up with another wire over to the fan. And then that fan switch goes over to our actual fan, meaning that our fan switch is dependent on the heater switch being on. So number 1 satisfies all those requirements. The heater can also be on when the heater switch is on because the heater is hooked up to the heater switch. It's a pretty straightforward one there. We have delta. Yeah, it's a lot of different things that have to be accounted for. But in this, just take your pen to the paper, get it going, and trace everything out. It's the easiest way to handle these ones. Number 25. An air conditioner will be installed on the roof of a stripped shopping center. The NEC requires that a 15 or 20 amp 125 receptacle be installed for servicing the equipment. The receptacle will be outside and exposed to weather. The receptacle is required to blank, have a weatherproof cover installed, be GFCI protected. All right, if we take a look at this and think about it logically, right? This is a convenience receptacle outside. All receptacles outside have to be GFCI protected. You can find that in 210.8b. It's either like 2 or 3 in the list. And then if we look at 1, have a weatherproof cover installed. It's outside, exposed to the weather. If it's exposed to the weather, it has to have a weatherproof cover. I believe that's a part of 406.6 or 406.8, something like that. Just protecting your receptacle from the weather. 406 is just the general receptacle section. And that's what that would be. But thinking about it logically, right, you don't want to have your receptacle just out there in the open. And you want to make sure that since there is the potential of water being around and it's a service receptacle used by us, it should be GFCI protected. It's a big one there. All right. We are halfway through here on 26. Give me just a second. I'm going to take a drink of water and then we'll hop back to it. All righty. Hopping into number 26 here. For the scenario above, the 2 heating elements are connected in blank. So if we take a look at the scenario, 26 and 27 are a part of this scenario, and we're going to be looking at the amps through each heating element for 27. But let's take a look at what this is actually asking. A pasta cooker contains two heating elements. Each element is rated at 5.8 kilowatts at 120 volts. The nameplate on the pasta cooker indicates that it can be connected in either 120 or 240. When it has this dual voltage rating here, 120 is our parallel connection. Sorry, I started writing before I actually spoke. Our smaller here is parallel. Our larger voltage is going to be series. This is always true. The smaller is parallel, the larger is series. In this case, the supply circuit is 240 volts. All right, if it's 240 volts, and we know that 240 volts is in series, 26 becomes real easy. It's a series connection. Bada bing, bada boom. Now, how many amps of current will flow through each heating element? Because we're in series, we want to find the resistance total and find our amps that way. Sure, we could try to figure out the amps of a specific element. That's not going to work though, because amps are additive, or amps are equal all the way through in series. Almost misspoke. So I total equals I1 equals I2. To find R total, to find that I total, I want to take R1 plus R2. To find R1 or R2, doesn't matter, they're equally rated. I'm going to take E squared divided by P, straight off our ohms wheel. Now, when finding the resistance of a single element, I want to use the nameplate. After I find that resistance, I throw away the nameplate voltage. So we have 120 squared divided by 5,800. I got 2.483. 9.931. Let me retype it out then. Oh, did you actually find the current? Oh, gotcha. Yep, 2.483. Now that's our resistance. If we want to find resistance total, I'm going to multiply that by 2 on my calculator. That's because R1 and R2 are exactly the same. And I got an R total equaling 4.966 ohms. Now that I have R total, I can use my E total, which is 240, and I can do E divided by R to equal I. 240 divided by 4.966. I got 48.329. 9 amps. So 48.33 is going to be our answer. All right, popping over to number 28 here. Number 28 is asking for which of the standard size disconnect switches listed below would be required for a 240 volt, 15,000 watt furnace. Assume single phase. So if we're just doing a regular disconnect switch here, they're rated in amps. So if we want to find amps, we're going to take P divided by E, 15,000 watts divided by 240 volts. We get an amp rating of I got 62.5. Perfect. Now, with disconnect switches, you want the next highest standard size of safety switch. That's because if I run 62 amps through a 60 amp disconnect switch, I don't have big enough fuses. That and then the busing isn't rated for it. It's going to become a hotspot and it's going to become dangerous. So you go to the next standard size, which is 100 amps. Just like a circuit breaker, right? If I want to run 62.5 amps, I'm not going to pick a 60 amp breaker. I want to size that up to the next one so I can actually run that current through it. Let's clear off this screen real quick. Pop on down. Number 29. For the scenario above, the boiler will supply blank watts of power. All good. All right, what do we know about power in series and in parallel? Power is additive. We take a look at our equations in both series and parallel. P total equals P1 plus P2. All we need to make sure is that the correct voltage is being applied to our elements. Let's take a look at the scenario. The nameplate on a single-phase boiler indicates that it can be connected to either a 240 or 480 volt circuit. 240 is parallel, 480 is series. In this case, the supply voltage is 240. We're in our parallel set. Each element is rated at 16.2 kilowatts at 240 volts. And then a boiler is simply a large water heater. If we're rated at 240 and we're connected in parallel at 240, I know that E total equals E1 equals E2. So the voltage applied to my elements is the correct voltage. If it's the correct voltage, I can take the nameplate as gospel. If P total equals P1 plus P2, then 16.2 kilowatts plus 16.2 kilowatts is going to equal 32.4. And if we convert that into regular watts, we get 32,400. Hold on. Why didn't it say that? Did I add something wrong?
No, we were told that that there was no answer. They messed this one up, so it's 32,400. No answer.
Okay. Gotcha. Yeah, that's I took a look at that real quick and I was like, what the hell? What's happening here? Let me double check the answer sheet real quick to see what they pulled this off of. Says D. Yeah, it doesn't even give you any math for it. It just says D. That's dumb. All right. Well, wrong question or wrong answers associated with the questions, I guess. If you do come across this and you're not 100% sure of something, just ask the question to your instructor. The worst that they'll say is, I can't help you with that. If it is something that you think the answer's not there, but it is, they might tell you, hey, the answer's there, just redo your math and check everything over. But yeah, if you're not sure, just do a quick check with them. Let's take a look now at our next question. which is number 30, for the scenario above, blank volts are applied to each element. This scenario is the nameplate on a single phase boiler indicates it can be connected to either 240 or 480. Again, series, damn it, I keep messing that up. It's parallel series. In this case, the supply is 480 volts. It's 480, so we're in series. The heating elements are rated at 16.2 kilowatts at 240 volts. All right. Voltage in series is E total equals E1 plus E2. Well, if they're equally rated elements, they'll see exactly the same thing. So really it's E total equals 2 times the voltage of 1. In this, we know that our voltage total equals 480. So if we take 2E1 divided by 2, cancel those guys out. And then if we do it to one side, we do it to another, 480 divided by 2, 240 volts are applied to each element.
Isn't that a combination circuit?
No, it's just 2 heating elements. So because it's just 2 heating elements, they're connected in parallel with each other. Because it's a series circuit, 480 volts.
But couldn't it be a combination circuit?
With just 2 elements, no. It would have to be either series or parallel. If you had more than 2 heating elements, you could get into a combination setup. IEC is not really going to be asking you that as much. That's a little bit more of a higher level math problem. So for these ones, just break it down to parallel or series. You don't have to worry about it being combination. If we had to worry about that, there's a whole lot of things that could come about in that instance.
Okay, thank you.
Yes, sir. Alrighty here. Now for 31, two 20 amp circuits share a neutral fed from a 120/240 volt single phase panel. If the ungrounded circuit conductors are connected to breakers 1 and 2, the following will happen when a 16 amp load connected to circuit 1 and a 14 amp load is connected to circuit 2. All right, I'm going to use this little panel schedule down here at the bottom to help explain. So circuit 1 and circuit 2 are both on A phase, right? If they're both on A phase, we can take a look at what's going to happen to the neutral. The neutral current is equal to the difference of 2 phases, A minus B, or if you're on the same phase, they add together. So because 1 and 2 are both A phase, they're going to add. So if I have 16 amps on 1 plus 14 amps on 2, I get 30 amps out of that. Let's take a look at our question here. One of the ungrounded conductors will be overloaded. Well, I hope not, because if we're hooking it up to a circuit breaker, then we're going to be hooking up that wire to that circuit breaker's rating. So if we hook up a 16 amp load, we should have 12 gauge there, not overloaded. 14, again, 12 gauge, we shouldn't have an issue. B, the grounded or neutral conductor will be overloaded. Well, this one's pretty likely because we're running 30 amps through the neutral. Let's take a look at C, see what else we have here. The 120 volt equipment could be destroyed because of the higher voltage applied. Well, we're not really applying a higher voltage. It's still 120 being applied to them. That doesn't change at all. So that's not going to be our answer. D, any of these? No. Not any of these because we took away A and C. E, none of these. Well, we still have B as a possibility. B is going to be our answer here. I do wish they would tell you what wires ran to it, but because they're specifying that they're 20 amp circuits, we are to assume that they are appropriately sized for that. So B, the grounded or neutral conductor will be overloaded. That's just because it sees 30 amps. It's a lot of amps. Clearing off these drawings, moving down to 32. 32 referred to the 120 240 volt single phase 3-wire panel board schedule shown in the figure above. If the black circuit conductor is connected to the breaker in space 13 and the red is connected to the breaker in space 11, excuse me, apologize for that. The neutral will carry blank amps when both loads are operated. This is going off of the same principle as the last question. The neutral amps is going to be the difference of A and B. So the difference of A and B, we need to figure out what those loads are. We have load 1 as 12.5 amps and load 2 as 375 watts. So we just need to convert load 2 into amps. For this question, we can take the nameplate as gospel because it's rated at 120 and we say that we're applying 120 to it. That's why I'm not going the resistance route. But if we take a look at 375 divided by 120, watts divided by volts equals amps, we have 3.125 amps. We can just take 12.5 minus 3.125, and we get 9.375 amps on the neutral. Number 33 here. The equivalent resistance of lamps 1 and 2 is blank ohms. So if we're looking for an equivalent resistance, that means that that resistance is probably combined in somehow. Let's see how it is combined. If I have one black wire coming in, hooking up to both lamps, and one white wire coming in, hooking up to both lamps, we're connected color to color in this case, or in parallel. There are multiple paths back to source. Because there are multiple paths back to source, then I know I'm in parallel. If I want the equivalent resistance, I take the resistance of a single lamp and divide it by the amount of lamps in parallel. So finding that resistance for each lamp, we're going to take RE squared divided by P. 130 squared divided by 300. I have 56.33. Yep. So in this 56.33, I can take that resistance and divide him by 2 because lamp 1 and lamp 2 are equally rated. I'm going to come up with 28.16 repeating. Which is 28.17. Now, for this, what we can do is go one step further. If you guys look at question 34, it's the neutral conductor carries blank amps on it. For this, all we need to figure out is how many lamps are on circuit 12 and how many amps are on circuit 10. To figure that out, I'm going to use my resistance. I already know the resistance of 1 and 2 is 28.17, and the resistance of lamp 3 down here is 56.33. That's just off on its own. So if I find how many amps for each of these guys, I can subtract and find the difference. First, I'm going to use my 28.17. To find amps, I'm going to take E divided by R. E in this case is going to be 120. 120 divided by 28.17 is going to give me 4.26 amps. And then if I do 120 divided by 56.33, this is going to give me 2.13 amps. Subtracting those out, I get 2.13 amps, and this is the answer for 34. B, right there. So saving those resistances and stuff, like writing them down on a piece of paper, can become really helpful. Especially if you have one question and then the immediate one after is just building off of that topic. Let's clear off these drawings and move down to 35. Refer to the information shown in the figure above. With all loads operating, excuse me, blank amps of current are flowing through breaker 1. So if we look at the scenario above, you are to install a 20 amp multi-wire branch circuit that is fed from breaker spaces 1 and 3. This is a 12240 volt single phase 3-wire panel board. The following loads connected are blank. On circuit 1, 20 feet of track lighting, 12 lamp holders. Each head has 75 watt 120 volt lamps, and then one quadplex preset with all of these loads on it. If we're looking for amps total, I know that now in all of these, our normal branch circuit wiring is parallel. That's because we want to maintain voltage as much as possible. So in all of this, I know that I'm hooked up in parallel because that's what normal branch wiring is parallel circuitry. Okay, so for that, now I can look, I'm rated at 120 all across the board. I'm applying 120, so I can take these nameplates as gospel. I know that in parallel, I total equals I1 plus I2 and so on and so forth. In this case, I'm just going to find the amps of each of these things and add them all together. So if I have 12 lamp holders at 75 watts, I'm going to first take my 75 watts divided by 120. I get 0.625 per lamp multiplied by 12 because I have 12 lamps, 7.5 amps. And then I can do the television and the receiver, just watts divided by volts. That's 350 divided by 120, 2.97 or 92, I apologize. And then 450 divided by 120, 3.75. And then the VCR DVD are exactly the same. So, well, as they are rated. We take 3.75 plus our 2.92 plus our VCR 2.1 plus DVD 2.3 plus that track light, which is 7.5. I got a total of 18.57, 18.6 when I added everything together.
Okay, I got 7.5. What's the other 2.92 and 3 point?
3.75. Sorry, let me clean those up a little bit.
Hey, thanks, appreciate it.
My pleasure. 2.92 and 3.75. All right, we're going to take a look at 36 here. I'll leave this up. Refer to the figure above. With the equipment energized, the power used by the elements connected to T3, T4 is 1.2. So T3, T4 is 1.2 kilowatts. The power used by the connected element at T5, T6 is blank. Let's take a look at the scenario here. This piece of equipment contains 4 heating elements that are equally rated to each other. Each has the same power and voltage rating. So if they all have the same power and voltage rating, they should be exactly the same. If this is 1.2, this is 1.2, this guy is 1.2, and this guy is 1.2. So our answer is E, 1.2 kilowatts. If they were to ask T1 through T6, these combined elements here, then you would just add those two elements together, because in parallel series, whatever, power is always additive. So you could just add those guys together. But in this case, they're just asking that single element. All of them are exactly the same. So it makes it super easy. All right, clearing off those drawings, moving on down to number 37 here. The neutral has been removed from the neutral bar. The circuit shown in the figure above has the equivalent resistance of lamp 1, 2, and 3 is blank ohms. So if we're looking at this guy here, we need to find out what this resistance is. For this, we're going to draw a new diagram because we don't have a neutral anymore. I'm going to draw my coil, which is representative of this breaker. This circuit 10 comes in, splits off to 2 lamps. Then it combines back together, goes to lamp 3, and then back to the power source. This right here is a combination circuit. What we're going to do is find the resistance of these two combined and then draw a new diagram. For this, we're using that 300 watt at 130 volt again. I believe that was, what, 56.33 ohms. All right, 56.33 ohms as each lamp. So if I have 2 lamps connected together here, that equivalent resistance is 23.16, right? Or 17.
It's 28.17.
Yeah, I don't know why 28.17.
No problem.
Boom. 28.17. So let's redraw this guy in our new state. We have 28.17 ohms for 1, 2. And then we have lamp 3 here with just a resistance of 56.33 ohms. Because we're in series here, I know we're in series because we have to go through both elements to get back to source. In series, our total equals R1 plus R2. So we add these guys together. And then that's going to get us our equivalent resistance of all three. What did you guys get for your total? Yep, 84.5. That's exactly what I got. Yeah, that's a little shy, but 84.5 is the roundup. Beautiful. Now, if we take a look at 38, 38 is also referring to this figure. The neutral has been removed, and the figure above voltage dropped across lamp 3 is blank, right? So voltage dropped across circuit number 3 here. If we have this final schematic in series, I know that I total equals I1, 2 equals I3 for this diagram here. It's all the same because it's series. So finding out what my I total is, let me change the color here. I total equals E total divided by R total. That total digit is going to be 240. It's 240 because we have two circuit breakers, 10 and 12 here. So if we're going phase to phase, 240. 240 divided by our 84.5 is going to equal what? .84 amps. Perfect. Now this is going to give us the amps overall. Now that we have one number to go off of, we can use the resistance of a specific element to figure out the specific amps. Or the specific voltage, I apologize. Because E equals I times R. So if I have I of 2.84 multiplied by resistance, and if we're looking for lamp 3, we're going to use the resistance in lamp 3, 56.33. That guy right there should see what? I believe it's 160. Is that right? Yep. 159.9, 160. That's your answer there. Clear off.
I got a question, sir.
Yes, sir. What's up?
Couldn't you just get the total resistance and then solve the total current, because it's a series circuit? So whatever current's flowing through 1 and 2 is going to flow through resistor 3 and 2.
Yeah, that's what we did right here. So you had to find this portion, this current total, to figure out what that voltage through 1 is, because that current total is the same throughout everything. And we need to find one number that we can answer the entire question off of. We got to compare apples to apples kind of a thing. That's why we had to find current total and then use the resistance of 1 to figure out the specific voltage of the lamp.
Okay, I guess you couldn't just say it's constant, because whatever current is flowing through 1.2 is going to flow through 3. But you're looking for the current, like the current drop or something? I don't know.
Oh, no. Question 38 is asking for the voltage drop across lamp 3.
Oh, my fault. I'm thinking current. I'm dumb.
Yeah.
Sorry.
No, I was almost there with you. I read the question. As soon as I finished writing that I total equation, I was about to say the answer's 2.84, and then I was like, oh, wait. We're looking for voltage. Yep. Wouldn't you subtract 160 from 240 to find the voltage drop. So voltage dropped is voltage applied to that lamp. I don't like the way that they say voltage dropped. Just because you start thinking of like your voltage drop calculation 2 kilo over CMA, but realistically in these questions, voltage drop is voltage applied to. It means the same thing. Can you just do peer to get through all of these or not? You could go through a peer chart and do everything. You would find exactly the same numbers. They would just organize themselves a little bit more. At the end, once I do get through all the questions, I'll do a peer chart so that everybody can get an example of that. And I do know we're at 7:20. Tutoring usually at 7:30, but I'll go as long as it takes for us to get through all the questions, that peer chart, and then I'll have a small portion of questions afterwards as well. Just so that you guys are feeling as comfortable as possible heading into this final. All right, clearing those off and heading on down to 39 here. Oh, my pleasure, y'all. 39 says the neutral has been broken in the figure above. The current through lamp J with the neutral open is blank. So if we're looking for J here, let's take a second and draw out this schematic. So if we're looking for lamp J current, what do we want to do? Well, we want to find the total current, I total. The reason for this is because if we redraw our schematic, combining lamps F through H, we can get a combination circuit with F, G, H, and J. This is series. And as we know, I total equals I1 equals I2 in series. So for this, now we just got to break it down into all the resistances. Each fixed resistance of the lamps equals 60 ohms. So if each of these lamps equals 60 ohms, I know that J equals 60 ohms. Now the combined resistance for F, G, and H is our parallel resistance. That's because F, G, and H are in parallel to each other. In this case, you could do 60 1 over x plus 60 1 over x plus 60 1 over x equals 1 over x, and then find your answer. Or because they're all equally rated, you can take the resistance of 1 divided by the number of them. So 60 divided by 1, 2, 3 resistors is going to equal 20 ohms. Now in this resistance total, because this portion is in series, F, G, H, and J are in series, my resistance total is going to be the resistance of 1 plus the resistance of 2 equaling 80 ohms as my resistance total. Now that I'm up in the totals and everything, I can do I total equals E total divided by R total. And in this case, because we're going from A to B, we have 240 volts phase-to-phase current, or phase-to-phase voltage, I'm sorry. 240 divided by 80. This is going to equal us 3 amps. And again, because I total equals I of 1 equals I of 2, I know that 3 amps are applied to J and 3 amps are applied to F, G, H. So if we're looking for current through lamp J, that's going to be B, 3 amps. 10 questions left, y'all. Let's see if we can bust through these. Clearing that off and moving down to 4041. 4041 says refer to the panel schedule shown above. If the neutral is removed from the neutral bar, blank volts will be applied to the TV. I'm also going to read 41. 41 says refer to the panel schedule in the figure above. If the neutral for this circuit is removed from the neutral bar, blank amps will flow through the freezer. All right. For this circuit, it originally looks like this. This is how it should look with the TV on 4 and the freezer on 6. But with our neutral bar removed, or with our neutral removed, we end up looking like this circuit. This circuit is series. I know it's series because I can start at one end. I have to go through both elements to get back to source. Series circuit. In a series circuit, what I want to do is find, first off, my resistances for each of these, then my resistance total. Using my resistance total, I can find amps, and then that's my apples to work off of for my whole circuit. Starting off with resistance for the TV, I can use my nameplate, 450 watts at 120 volt. So I'm going to take 120 squared, divide by 450. And then the nameplate for the freezer is 7.5 amps at 120. So 120 divided by 7.5. That'll get us our two resistances. Pop those down in the chat once you have them. Yep, I got 32 and 16 as well. 32 ohms and 16 ohms. Now in series, R total equals R1 plus R2. So for this, if we add 32 plus 16, we're going to get 48 ohms total. With our 48 ohms total, I can then go over to I is equal to E divided by R. In this instance, we're at a 120 to 40 volt panel. So if we go phase to phase in this instance, if we lose our neutral, we're going to be sitting with 240 volts. 240 volts divided by 48 ohms. Be like 6, right? Oh, 5. 5 amps total. If we have 5 amps total, first off, we can answer 41. Boom, 5 amps. Easy peasy stuff. Now, with our TV voltage here, because we're looking for volts, we have amps, an easy spot to work off of. We know that volts is equal to amps times resistance, ohms. I'll take my 5 amps multiplied by my 32 ohms for my TV specifically. 5 times 32, I believe is what? 160? 160 volts. Beautiful. Number 42 here, we're going to take a quick look at while we're still on that page. I'm going to keep that math up on the right. Number 42, each battery outputs 6 volts. Voltage supplied to the load is blank volts. Let's write in 6 for each of these. 6 volts on each of the batteries. Now I have two things. I have my parallel voltage, which is E total equals E1 equals E2. It stays the same. And then my series voltage is E total equals E1 plus E2. In these, for batteries, kind of like our regular AC voltage, if it's color to color, it's parallel. If it's like black to white, then it's series. In batteries, that translates to if it's the same charge, it's parallel. If they're different charges, it's series. So looking at this top set here, I have a positive to negative connection. So I know that these two batteries are in series, just like this bottom set, positive to negative. This bottom set is in series. But if I take a look at my top set and bottom set, I can see I have positive to positive and I have negative to negative. So I have series, and then parallel connected to the two. What we're going to do is add the voltages that are in series, and then they stay the same in parallel. So if I have 6 and 6, that's 12 volts for my top set, 6 and 6, 12 volts for my bottom. Those two voltages will be the same going to the load, so I am applying 12 volts. All right, clearing off that page. Moving on to 43. We're at the last page, All right, let's push through. 43, refer to the figure above. The total resistance of the circuit is blank ohms. This figure is true for 43 and 44, so we're going to take a look at them together. Now, first, we have a whole bunch of wire spaghetti here. Wire spaghetti is never fun, and it's never helpful. So let's take a look, draw out this diagram in a ladder diagram format, make it easier to understand. I'm going to start with a power source. My power source is this 208 volt circuit. I already see that I come in and I jumper to two spots. Come in, jumper to two spots. So I already know that my black comes in and jumpers 2 times, and my red comes in and jumpers 2 times. Let's figure out what's going on between those jumpers, shall we? For my first set, I can come out to L1. I have to go through my element and come back to L2. Now I have a tiny little nib that jumpers over to L1 on my second resistor. And then I come back on the red. That red is connected to the red going to my power source. So I know that that black jumper comes in, goes to R1, little tiny jumper, and then it goes to R2, and then goes back to my power source. This is the same exact thing for R3 and 4. That black jumper comes in, it goes to R3, little tiny nib jumper goes to R4, and then back to my power source. Now that I've broken this down into a little bit of an easier diagram to understand, let's take a look at what's going on our circuit. So 1 and 2 here, I have to go through 1 and 2 to get back to my source. These guys are connected in series to each other. Same thing with 3 and 4. These guys are connected in series with each other. So if I redraw my diagram, I can do 1, 2, and I can do 3, 4, just like that. Now I have a parallel diagram here, and my parallel rules will apply. Now that I have this basic setup of my ladder diagrams to work off of, let's fill in some actual information. Each element is rated to deliver 2,200 watts at 125 volts. Sounds good, Connor. Enjoy. Man, that sucks having to work at 7:30 on a Wednesday or a Sunday. I don't know why I was about to say Wednesday. Let's keep the weekend, god damn it. All right, let's figure out the resistance of each element here. I can do that by doing E squared divided by P. That will equal R. 6.545. I like it. Now I can apply this resistance to each of my elements. In doing that, because I'm series connected for 1 and 2, 3 and 4, I can add those two together. If I add my resistances in the series, I'll get 13 point what? 09?
7.1 for resistance.
7.1?
Yeah. 125 squared over 2200.
Yeah, that is. Damn. Let me erase these. 2, 2, 2, 2, 2, 2. I must have. Oh, I probably did exactly the same thing as you did because I got the same resistance. Yeah, taking a look, making sure that we're putting in 125 volts. That nameplate rated. Said 7.10. We'll just stick with 7.1. That gets us our combined resistances of 14.2 for each of these sets. Now, if we go through and find our R total for our circuit, I can take our 14.2, press 1 over x plus 14.2, 1 over x equals, and one last time 1 over x, I'm going to get an R total of 7.1 ohms. Lot of stuff going through just to figure out that the resistance of 1 is the resistance total. This is a special square. I've talked about this before, but I'm not going to get too into it. Just go through all of your same rules. You don't have to try to figure out this answer any quicker than we already are. 7.1 ohms total. It it only looks so easy just because I do it all the time, man. I have so much practice in this, and hopefully you guys will be able to get into it as well and be able to practice a whole bunch on top of it. I've been tutoring first year material since I was a second year, which makes this almost 4 years total, 3.5 years been doing it. Oh yeah, once you guys are third and fourth years, this is going to seem trivial. All right, the total heating element will deliver blank kilowatts of power. If we're looking for totals, we can use that resistance total and our E total to find our power. So P equals E squared divided by R. Our E squared at this is 208 squared. So that's the actual voltage we're applying. 208 times 208 equals 43,264 divided by that resistance, which is 7.1 ohms. I got 6,093, which if we convert into kilowatts would be 6.092. If you have watts and you're converting to kilowatts, just divide by 1,000 if it makes it look a little easier. All right, for these last questions, we have a lot of deration and conduit fill, it looks like. So there's a couple of ways that we can go about this. starting with 45 here. Trade size blank, the minimum size schedule 40 PVC that can contain 13 each 8 gauge copper THN, THWN conductors. If we're looking for a conduit with all the same size conductor, we want to use Annex C. Same thing with number 46 here. Oh, wait, no, 46 is opacity. Disregard. So 45 Annex C is what we're going to be going to. Let's take a look at our code book. We're going to go all the way to the back in chapter 9. I don't know why I'm scrolling. Gotta click and drag this one. All right, and if we're looking for PVC, I believe is C9 or C10, somewhere down there. Elephant C. 9 is RMC. Oh, it's C13. $790. I'm at $797. Sure, it's C13. This is so much harder in. Okay, so it's C11. Yeah, table C11. Boom. Rigid PVC schedule 40. Schedule 40 is what we want to be in. We want to scroll down to THHN, THWN, number 8 right here. And if we go to 13 of them, the next highest size is 16, which is 1.25 inches. This one's just taking a look at the table and going through it. Always use 5, never 5A. Never use table 5A. Table 5A is trash. Doesn't help you whatsoever. Did I accidentally use 5A? Am I being a hypocrite? I don't think I am. Yeah, I
Where is
used the right
table
one.
5A?
Huh?
Where is table 5A?
Table 5A is in chapter 9. It's before the annexes. So if you look at the top here, do you guys see the NEC right now? Yes, okay. So if we're looking at the top of this, this is saying the maximum number of conductors for this specific raceway based on chapter 9's table 1, table 4, and table 5. This is just saying that they already have done the calculations for us. Instead of us breaking out our table 5 and table 4 to answer this question, table 5 giving us the circular mills for, or the area for each of our wires plus insulation, and table 4 telling us the cross-sectional area that we can take up. This is just a pre-done map of everything so that we don't have to go through all of the extra math. Table 5A is for compact copper, which is not what we use. We use regular stranded or solid copper. Compact copper is like that super fine stranded stuff that you can find in like fixture cords and things like that. Have a good night, Ben. All right, let's pop back over to this review.
Hey, thanks.
My pleasure. All right, now 46, the ampacity of a 10 gauge THHN, THWN copper wire in a conduit with 7 other current carrying conductors is blank amps. Let me write this out. So corrected amps is equal to table amp multiplied by temp D rate multiplied by number of wire D rate. In this, its table amp is 310.16. Temp D rate is 310.15 B1. Cross out B2. Do not use B2, just B1. And then this last one here is 310.15 C. If we look at the table of 310.16 for 10 gauge, we get 40 amps. This is in the 90-degree column. Remember when I said that if we're looking at 310.16, the terminations out of the 75 and derate out of the 90, we're derating the wire, so we're going out of the 90-degree column. Now, if we look at our next criteria, temperature derate, they don't give us temperature, so we're just going to put 1. If they don't give us anything, we just put a 1 in there. It doesn't change the answer, but it makes sure that we account for it. Now, if we look at 310.15C, the number of wire derations, we can look at if it's over 3, then we have to go off the table. 4 to 6 is 0.8, an 80% deration. And then if we look 7 through 9, tells us that it's a 70% deration, 0.7. So all we have to type into our calculator is 40 times 0.7. What does that equal for us, y'all? $28 amps. That's what I'm liking. 28 amps is our adjusted ampacity for that. All right, now we can go to 47, almost exactly the same thing, except you can see the last sentence says, don't forget to use the 90-degree column in NEC table 310.15B16 for ampacity correction. Has anyone been able to find a 310.15B16? If you're looking in the 2020 or 2023 code, it ain't there. You want to know what it is? This table, 310.15B16, is 310.16. 310.15B16 is what the table used to be called in the 2017 code book. So they forgot to update this question, but it's 310.16. That's the same exact table. They just call it something different because they were tired of calling it that big old thing. All right. Same exact setup here, right? We're going to be using our same exact formula. And if we take our table amps for 10 gauge, 40 amps, just like we found. Now, if we go to our 8 current carrying conductors, we have that 0.7 again. Now, our 139 degrees Fahrenheit, we have to go over to the code book and figure out what that is. Ah, there we go. Nope, I'm looking at the right one. 310.15B1 Fahrenheit 139 falls in between 132 and 140, which is 0.71. Nice. All of that information was erased, but it's going to be 40 times 0.71 times 0.7. Type this into the calculator. You can do times 0.7 or times 0.71 first. It doesn't matter either way.